Okay, so previously we learned the relationship between energy of a photon. Okay, relationship between energy of a photon and the frequency of the photon. So we learn that the higher the frequency, then the higher the energy of the photon. Okay, now here we want to discuss what is this continuous spectrum. Okay, visible light spectrum that is continuous, and also this line spectrum. Okay, what is this line spectrum actually? Okay, so basically what happened here is that, okay, first, how do we get this continuous spectrum? Okay, we learned that if we want to get that continuous spectrum, we can, okay, if we have a glass prism, and then shine a ray of light into the glass prism. Okay, so what happens is the ray of light, when go into a light prism, the ray of light will disperse. Okay, it will refract and disperse. So basically, the light will spread out. Okay, spread out into different color, and when the light come out from the glass prism, it will spread out even further. Okay, so we will be able to get a spectrum of different color. Okay, spectrum of different color. So this is how we get the continuous spectrum. Now, how about the line spectrum? Okay, how about the line spectrum? Okay, the line spectrum is produced basically by detecting what are the radiation that are emitted by a certain element. Okay, emitted by a certain element. We know that every different element, okay, the atom of every different element, they have a different composition. That means they have different number of proton, electron, and neutron. Okay, all different number. And when these atoms, okay, they have energy, they will oscillate. Right now, okay, they will oscillate. So when they oscillate, that means they will release electromagnetic radiation. Okay, release or emit electromagnetic radiation. Okay, now you see, let's look at the simple structure of the atom. Okay, we have the nucleus, and we have electron orbiting around the nucleus, right? Okay, orbit in a different shell. Okay, different shell. Okay, different electron shell. Okay, so the electron that is nearer to the nucleus have a different energy level compared to the electron that orbit at a at the level that is further away from the nucleus. Okay, so which one is it that have more energy? Which one is it that have less energy? So for your information, the electron that orbit at an electron shell that is nearer to the nucleus is the one with the lowest energy level. Okay, lowest energy level, while the one that orbit the furthest away have the highest energy level. Okay, why like that? Because we know that the nucleus have proton, and proton is positive, right? Electron is negative. So the proton and the electron, they will want to attract each other. So if you are nearer to the nucleus, that means the amount of energy that you have is less, because you are being pulled nearer to the nucleus, so you have less energy lah. So if you gain energy, okay, when an electron that is near to the nucleus, they gain energy. Okay, electron, they gain energy. When they have enough energy, they will be able to be excited. Okay, the electron can be excited, and when they are excited, they will be able to jump from the an electron shell of lower energy level to an electron shell of higher energy level. And when they gain more energy, they will be able to jump even more. Okay? So different electron shell, they have different energy level. So what happens, and when the electron gain energy, they jump up one level, What happens if they jump down? If they go from a higher energy level and they drop to a lower energy level? They have a lot of energy, right? So when they drop down to a lower energy level, what happens is the energy will be released. Okay, that energy will be released as electromagnetic radiation. And the energy in electromagnetic radiation is, of course, carried away in the form of a photon. Okay, carried away in the form of a photon. So that means the electron that drop down from different electron shell, they will have different energy levels. So that means the photon that is released will have different amount of energy. And different amount of energy means the frequency of the photon will also be different. Remember this relationship between the energy of photon and the frequency. Okay? If the energy is higher, then that means the frequency is higher. The frequency of the photon will be higher. So that means every different atom will be able to emit photon that is at a different frequency, because different element, they have atom of different composition, right now. Okay, so by detecting the type or the frequency of photon that is emitted, okay, what is the frequency of photon that is emitted, we will be able to identify what type of atom is this, what element is it that is exists within a certain material. Okay, so let's say you found a piece of metal. Okay, you found a piece of metal. You want to know the what is the composition, what is the element that is contained within that metal. So what you can do is you can first heat the metal first. Okay, heat the metal. Okay, let the electron gain energy, and then after that you detect the electromagnetic radiation that is emitted from the heated metal. So the frequency, the different frequency will give us this line spectrum. Okay, they will give us this line spectrum. Why is it that it looks like lines? Okay, because like what we learned is that photon carry a specific amount of energy, and that specific amount of energy will mean that the frequency will also be specific. Okay, it is the photon that is emitted is in a specific frequency. So that is why we see that, okay, if the photon that is emitted is in this frequency, then it's only in this particular frequency. It will not be like a spectrum of different frequency. Okay, if this frequency, everything in this frequency, this frequency, everything in this frequency, and so on. Okay, specific frequency due to the specific amount of energy inside the photon. This is of course only possible if the energy, if the light energy, if the energy of light is transferred in discrete form. Okay, which again, this is a proof that show that the light energy is transfer in discrete form. Okay, in light packet that we call light energy packet that we call photon. Okay, so this is how we get the line spectrum. Okay, so from the line spectrum we can identify what are the elements that are available inside a certain object, and astronomers can also know planets that are very far away. What kind of element is it that exists in that planet? Okay, without going to the planet, they can know the planet contain what element. Do they contain oxygen, carbon dioxide, or whatever? Okay. So let's look at what is written here. Okay, so the dispersion of white light by a prism produces a continuous spectrum consisting of 7 visible colors. This spectrum has a wavelength range from 400 nanometer to 750 nanometer. The visible light spectrum is said to be continuous because there is no separation gap between each color in the spectrum. Okay, you see the reason why is it that this the light that is dispersed, it looks like it is in a continuous spectrum, because white light consists of photon of different frequency. Okay, many photon in many different frequency all mixed together, so they produce white light. Okay, they produce white light, but each and every frequency inside here consists of photon that have a discrete amount of energy. Okay, and the reason why is it that it looks like it's continuous is because the difference in the amount of energy is very small due to the small value of Planck constant. Okay, Planck constant is 6.63 times 10 power by negative 34. Okay, by negative 34 joule second. So you see this number that is extremely small. That means when there is a small change in frequency, the small change in energy will be the change in energy is even smaller. So you can get a spectrum that looks continuous. Okay, because the changes are so small that you cannot see the difference. Okay, you cannot see the difference. So it looks like a continuous spectrum. But when you detect electromagnetic radiation that come from specific elements, come from a specific atom, then you can get a line spectrum. Okay, line spectrum. Because the atom does not emit radiation in every single every frequency. Okay, only specific frequency that is emitted by the subatomic particle inside the atom. Okay. Okay, so continue. So the light spectrum produced by an excited atom is a series of colored lines with unique wavelength and frequency. Each element produces a spectrum with a series of its own distinctive line. Therefore, the line spectrum can be used to identify the presence of an element. So table 7.1 show the frequency and quantum of energy value of the line spectrum produced by a mercury vapor lamp. Okay, so this is the line spectrum that we get from mercury vapor lamp. So if you use a different element then other than mercury, then you will get a different line spectrum. Okay, so the line spectrum is also called like the fingerprint of elements. Okay, fingerprint of different elements. Alright, so here we can see that line spectrum color is violet. So violet have higher frequency, right now. See, high frequency. Yellow-orange, the frequency is low. Okay, so that means that the energy quantum of the photon will be higher for violet. Okay, so high energy. This one, yellow-orange, the photon contain a lower amount of energy, low energy. Okay. Okay, next let's discuss this example. Okay, compare the energy of a 400 nanometer and a 750 nanometer light photon. Okay, so we have the wavelength. Okay, this is a wavelength. Okay, but if you want to calculate the energy, okay, okay, we need the Planck constant and also the frequency. So how is it that we can get the frequency? Okay, we can calculate the frequency by using the wavelength. From wave equation, wave speed equals to frequency times the wavelength. So the frequency will be equals to the wave speed divided by the wavelength. And these are light photon, light. So that means the speed of light, that means the wave speed is speed of light. And the symbol that represents speed of light is c, a small c. So over the wavelength. So we can get that the energy will be equals to Planck constant times the speed of light over the wavelength. Okay, so we put in the value. Okay, so equals to c over wavelength. So the Planck constant is 6.63 times 10 power by negative 4. Speed of light 3 times 10 power by 8. And then the wavelength is 400 nanometers. So 400 times 10 power by negative 9. And then you will be able to get, I think you can calculate this yourself. Okay, you can calculate this yourself. So how many joule? Okay, how many joule is the energy in 400 nanometer light photon? Okay, next is the 750 nanometer. So energy equals to, okay, we straight away use okay, Planck constant times the speed of light over the wavelength. So we can get Planck constant 6.63 times 10 power by negative 34, okay, times 3 times 10 power by 8. And then over the wavelength. Okay, the wavelength is 750 nanometer. So 750 times 10 power by negative 9. Okay, nano negative 9. So you can get how many joule of energy. Okay, so this one, the energy is 4.9725 25 times 10 power by negative 19 joule. Okay, and this one we get 2.652 times 10 power by negative 19 joule.